So the AC method starts out in the same way that our blind guessing and checking started out. I'm going to draw in this empty factoring grid. And I'm going to put in here my 2x squared. And I'm going to put in here my minus 3. But we don't, as we did in our previous guess and check approach to this, we don't leap directly to taking this term and breaking it apart. Even though in this example we could, because there's only one way to do it. In other examples where it's more complicated, such as the ones we'll see next, we don't, for obvious reasons, we don't want to lock ourselves in to one of those factorizations or another. So instead, what we end up doing in the AC method is that we first play a sum and a product game. But here's the difference. When our leading coefficients were just equal to 1, as they were in our previous examples that you worked on in that table at the beginning of class, when this leading coefficient wasn't here, right, then all we had to do was find a pair of numbers which multiply together to give me that, and which add together to give me that. Since that doesn't work off the shelf when the leading coefficient is not 1, we just change our sum and product game a little bit, and here's how. We're still going to be asking the question, find me a pair of numbers which multiply together to give me such and such, and which add together to give me such and such. The difference now is that while what they add together to give me is still going to be the same, so that middle coefficient, the coefficient of the linear term, -5, that's still going to be my target for the sum in my sum and product game. The difference is in what my product target ends up being. Whereas before, it used to just be the C coefficient. That's what we call this constant over here, just for the sake of terminology today. In a quadratic trinomial, the 3 coefficients, respectively of the x squared term, the x term, and the constant term, are traditionally called A, B, and C. Those are just the names that we often give to those coefficients, particularly when we're using the quadratic formula, which we'll learn at the end of the semester, to solve an equation that involves a quadratic trinomial. We borrow this lingo from that. So in the original sum and product game, we were always just looking for C, that constant, to be the target of the sum and the product game. That doesn't work when the leading coefficient is not 1. So what we do instead is we multiply together C, which is the constant coefficient, times A, which is the leading coefficient. And so we want the product not to equal just C, but we want the product to be C times A. So what is C times A for this polynomial? 2 times -3 is -6. So we just play a modified sum and product game, where the sum is B, the middle term, but the product is not C, but A times C. The leading coefficient times the constant coefficient. And now the question is, what pair of numbers multiply together to give me -6, but also add together to give me -5? The pair that we want is 1 and -6. 1 times -6 does give me -6. 1 plus -6 gives me -5. So we play the sum and the product game with AC as the product and B as the sum. And in this example, we have a winner, 1 and -6. And now that we've played that modified sum and product game, what we do with our winning pair is we use that pair to split the middle term. And what I mean by split the middle term is that this 1 and this -6 are now telling me what I'm going to fill into these 2 boxes. Right? So if you remember, working backwards, we know that when I add, I combine the like terms inside of my grid. I know that my 2x squared doesn't have a dance partner, and so it just carries over into a 2x squared. My -3 doesn't have a dance partner. But working backwards, I know that my 2 other boxes have to add together to give me the -5 that I'm looking for, -5x. And so what this winning combination here is telling me is that that -5 is going to come from a 1x and a -6x in these middle 2 boxes. So that's what I'll fill in. Here's another piece of good news. It doesn't matter which one I put where. That's another advantage to this systematic approach to factoring instead of guessing and checking and groping around in the dark. It really does not matter where I put which one I put the 1x in, which one I put the negative 6x in. Because we know now that if we can fill in the first row and the first column of this grid in a way that produces these four products, then when I combine them together, I'm going to get 2x squared minus 5x minus 3. And the magic of the AC method is that if we have won the sum and the product game, and if we found the right pair that does these two things, that it multiplies together to give me AC and adds together to give me B, then it will be possible for us to fill in the upper parts of this grid. And so then our last piece of this technique is figuring out how to do that. And here's how I like to do that part. How I like to do it is by starting with picking a single row or a single column of my table. And just for fun, I'm going to choose the first row here as the row to focus in on. And what I want to do to that first row is I want to factor out the greatest common factor of the first row of my table. So then my question is, what is the greatest common factor between 2x squared and 1x? So 1 is the greatest common factor between their coefficients. That gets us started. And how many powers of x are in the greatest common factor between 2x squared and 1x? How many x's do they have in common? They have a single power of x in common. So the greatest common factor between these two terms is 1x. Or if you like, we can just write that as x. So I factor out the greatest common factor of the terms on my first row of my table. And what's great about that is as soon as I have this factor, I also now are going to know what these two factors have to be. If I factor an x out of 2x squared, what do I get? 2x. And when I factor an x out of my 1x, what do I get? I get 1. And so then that tells me my first factor, 2x plus 1. Now all I have to do is fill in this last empty square. And I can do that just by asking, well, 1 times what is going to give me negative 3? Factor a 1 out of negative 3. I get negative 3. And now we're right back to the factorization that we discovered when we were groping around in the dark. 2x plus 1 times x minus 3. But we arrived at it in a much more systematic fashion. This is a fashion that A is repeatable. Any quadratic trinomial with a non-trivial leading coefficient that can be factored over the integers can be factored in this way. And also, it completely eliminated, it didn't even minimize, it eliminated our guessing and checking. We didn't have to worry about how to split that 2x squared apart. We didn't have to worry about how to split that 3 apart, except insofar as we had to maybe do a little bit of mental guessing and checking to win the sum and the product game. But that's no different than the guessing and checking that we would have to do mentally in the case where the leading coefficient was trivial, the cases that we started the class with today. So I like this method a lot. I also find that this particular presentation of it kind of pulls from a lot of different sources, and most textbooks don't clean it up and make it a factoring lattice in this way. But because the lattice is such a powerful tool, I really, really like this as my frame. It's my go-to. And I learned the AC method as part of teaching this course a couple of years ago. So it's something I wish I had known 15 years ago or something. But because it's so nifty and it's so powerful, I learned how to do it, loved it, and then I also adapted it to use this lattice method. This, to me, is my go-to method for these. So this is an example that's going to stretch our AC method a little bit. And in particular, it's going to stretch our ability to win the sum and product game. So let's see the method in all of its glory. Why I like this example better than the first example that we looked at is that if we were just guessing and checking, we would have a lot of guessing and checking to do. Because first of all, this 15, if we were to put this 15x squared into the upper left-hand corner of my cell, I could split that 15 apart really in 4 different ways. I could put 15x and x. I could put 5x and 3x. I could put 3x and 5x. I could put 1x and 15x. Right? So that 15 has a bunch of different ways that we can break it apart. Similarly, the 8, the constant term, has a bunch of different ways I could split it apart. A 1 and an 8, whoops, I could split it into a 1 and an 8, a 2 and a 4 and a 2, an 8 and a 1. Right? And because there's a plus here, I could also put negative signs on none of them, or I could put negative signs on both of them. So there's a lot of different guessing and checking we would have to do if we were using guess and check for this. So let's see how AC method helps us to do that in a more systematic fashion. So the first thing that we do in the AC method is we instantly want to play the sum and the product game. First of all, what are A, B, and C in this example? So remember, in whatever context we see them in quadratic expressions and equations, A is the leading coefficient, the coefficient of the x squared, B is the first order coefficient, and C is the constant. So C stands for constant, if you like. And so in my sum and product game, I need to find a pair of numbers which add together to give me B, so they need to add together to give me negative 34. But that same pair of numbers also needs to multiply together to give me how much? This is the part that puts the AC in the AC method. We don't take just 8, as we did before. We take 8 times 15, namely 120. So the degree of difficulty on this factorization problem is that we have a number, 120, that we need to find a pair of numbers which multiply together to give me 120, but which also add together to give me negative 34. And there's a lot of different pairs of numbers that multiply together to give me 120. 120 times 1, 60 times 2, 30 times 4, 15 times 8. We could keep going. But I already ran across in that list one pair that sounds like it might fit the bill. How about 30 and 4? 30 times 4 is going to give me 120. But when I add those two things together, I don't get negative 34, I get positive 34. So how do I fix that? I need some negative signs in here somewhere. Where? Yeah, I need a negative sign on both of them. After all, their product needs to be positive, and therefore the two numbers have to have the same sign. So negative 30 and negative 4 does win the sum and the product game. And that takes care of step 1 in our use of the AC method. So now with that negative 30 and that negative 4, let's go back to our grid. We know that when we add together the like terms in my grid, the 15x squared and the plus 8 are not going to combine together with anything, but the other two terms will. These two terms will add together with one another to give me that middle term that I'm looking for, and the middle term that I'm looking for is negative 34x. And the game that we just played showed us that what we want to do is split it into a negative 30x in one square and a negative 4x in the other square. And if I do that, now the AC method is going to guarantee that I can actually fill in the first row and the first column of my grid in a way that produces these four products. So how do I figure out how to do that? Well, the way I like to do it is just by focusing in on one row. I could focus in on the first row, but actually just to switch things up, I just want to convince you that this would also work if I focused on the second row instead. Because I don't like thinking about 15s and 30s. I'd rather think about 4s and 8s. What's the greatest common factor between negative 4x and 8? Yeah, this one's nice because the answer is just a single number, number 4. So 4 is the greatest common factor between those pair of terms. And now, if I factor a 4 out of these two terms, what am I going to have left over? A 4 factored out of minus 4x is going to give me negative x, and a 4 factored out of this 8 is going to give me a 2. Okay, so far so good. Now the only last thing I have to fill in is this square right here. And the easiest way to fill it in probably is just to think about what do I have to multiply by 2 in order to give me negative 30x? Negative 15x. And sure enough, we can check that negative 15x times negative x is going to give me positive 15x squared. So this is one solution to this factorization problem. This is equal to minus x plus 2 times minus 15x plus 4. It's kind of a weird, clumsy solution, to my eyes anyway, since I look at a lot of factoring problems, because I'm in the line of work that I'm in. It's kind of a weird solution, because both of my x terms ended up with a negative coefficient stuck on them. It's not the end of the world. Clearly it works. And if I were trying to solve an equation that had this on its left-hand side and a 0 on its right-hand side, I could still split these two factors apart, give them their own separate equals 0, and solve each of them using the methods for solving equations we learned at the beginning of the course. We could still do that. It's just, to me, to my eyes, this looks a little bit unnatural. And the reason for that is that by choosing the second row here to factor out this negative sign, which was attached to the minus 4x, I could have factored that out at this stage, but we chose to just leave the greatest common factor as positive, because we usually do. But if we had made the other choice, if we had followed the advice in the list on the right, list of steps over on the right, we would have keyed in on the first row instead of the second row and asked, what's the greatest common factor between 15x squared and minus 30x? And how would you have answered that question? Yeah, the 15 would have been the greatest common factor between the coefficients, and the x would have accounted for the greatest common number of x's between these two terms. Then if we factored out 15x from 15x squared, we would have gotten a single x, and from negative 30x, we would have gotten a negative 2. And then negative 2 factored out of positive 8 would have given me a negative 4. And so it would turn out that doing it this way, the factorization we end up with has positive coefficients on our x's, x minus 2, 15x minus 4. But the great news is all roads lead to Rome. And in fact, both of the factorizations that we just wrote down are algebraically identical. And just to convince you why, just as a parting shot here, why these two things are the same is we could imagine factoring out a negative 1 from this first factor. And if I factored a negative 1 out of that first factor, we would have ended up with a x and a negative 2. And if I also then did it from the second factor, factor a negative 1 out of those two terms, we would have ended up with a positive 15x and a minus 4. But then if I were to rearrange these factors to get these two negative 1s together, I'd get a negative 1 times negative 1. And what's that going to do? That's just going to go away and become a 1. In other words, that multiplication ends up being invisible. And when that happens, there is no longer a difference between these two factorizations. So that's the good news. I don't mind either of these two answers as your final answer to a problem like this. There's a lot of work that goes into getting either one, and the expressions that you get are algebraically equivalent. But just stylistically, I'm used to seeing answers that look more like this. And it may be the case that web work or other online systems, or maybe your professor next semester might have a preference for one over the other. So just know that the choice that you make when you actually factor out a GCF from a row or a column in your factoring grid can have that kind of weird unintended consequence. It doesn't always, but it could.